there. It's like, when you're solving equations, you're using algebra or calculus. We don't start with algebra. We're solving a particular problem, coming up with a solution, but underneath it we're using algebra or calculus. So it's the same thing with stats. We did a basic stats 101 yesterday. You should do linear algebra and math, but then you go ahead and apply that to solving problems, solutions, and in our case, business problems that involve data sets, deep learning algorithms, data sets, and the actual analysis involves as well. So that's why we did spend a little bit of time on the theoretical side of yesterday, and now we'll get more practical and applied. It will become applied. Machine learning is actually applied. And then just quickly running through these slides, 5 minutes, just to recap, we looked at data structures, different types. We realized it was quite a formalize this stuff and give everything exact definitions, which is always a good thing. And then because it enables us to set up the foundation, build on that afterwards. And what a data structure was, types of data structures, tables, graphics, arrays, and lists. And then we move straight onto algorithms, and for that an algorithm operates on a particular type of data structure, determined from the data itself, and how it's processed, produces data. And so these are algorithms, and then we homework-related reading. We'll look at these things a little bit, to Nicholas' questions at the end. And then we looked at computation, something called complexity, and we saw that another name for it's a way of analyzing algorithms for their efficiency, and we also saw that order of the algorithm, complexity. So it was 3 different ways of looking at the problem, which is basically how efficient is an algorithm given a set of 10 inputs. How many steps does the algorithm take from solution? 10 steps, where does it complexity? And I think if we follow up, look at different orders, constant, log-in, integrate, etc. Factorial. So 10 inputs, 100 inputs, 100 factorial. It's a very large number, and we sort of hope that if we see that, we realize that our problem is probably intractable using that algorithm. Really, not in a theoretical sense, but in a practical sense. We're going to need an awful lot of resource in terms of compute, memory, and time. So, we're always happier when the algorithms are in order of increasing time. We're always happier when further up that list we are. Constant doesn't really happen, but log-in happen. So we're much happier when we use less resources further up. Here's a nice graph showing that. So, log-in is about have 100, n equals 100 inputs, and the people log in at 100 to this of curve n. Or to this about 8.5 to the power of 84, 9, 128. That's why that graph at 100 is around 8, 9. It's just math. So, but the point here is that it flattens out rather quickly. We always hope that our algorithms log in with a very not less resources, scale up to n equals a trillion quite well, log in at a trillion, something like maybe 1,000. What's the power of 1,000? Without the calculator, right? But, it's not bad. 1,000 is okay. There's just 10. We have a trillion inputs. We have a trillion operations. That's not so good, really. In today's compute, it's not so bad either. But a trillion is hardly 1,000. Right? And then it just gets worse from there. N log n very quickly. large number of created, still an active field. People are still, trying to find more and more efficient algorithms all the time. They don't know if they've got the most efficient algorithm to solve a certain problem, unless you theoretically prove that this is the most efficient. Theoretical computer science. Then we fit towards solving the problem. But yeah, algorithm is how it's called evolutionary because help. Yeah, just machine learning. Okay, just machine learning. That's a little bit confusing actually. So, second phase, like start straight off in the head.